Good morning, Year 12s, and welcome to another exciting episode of welcome to Methods. Okay, so I just want to quickly go over whatever I didn't cover yesterday, which was using the product rule. So let's have a quick look. So in this case here, I've got two functions. U equals e to the x. It's a bit big. V equals 2x squared plus 1. U dash is e to the x. V dash is 4x. The product rule is you multiply those acrosswards and you multiply those acrosswards and add them. So here I'm going to get 4x e to the x plus, because I've got two things, 2x squared plus 1 e to the x. We can multiply it out. 4x e to the x plus 2x squared e to the x plus e to the x. Of course, we can take out e to the x as a common factor. So we'd have 2x squared plus 4x plus 1. And don't forget you can check it on your CAS. So what was our original? E to the x, 2x squared plus 1. So, good habit to get into. E to the x, 2x squared plus 1. Highlight d dx, enter, simplify, there it is, 2x squared plus 4x plus 1. That's our first one. Okay, this one looks a bit nastier, and it's disappeared. Okay, so u equals e to the x. Of course, du dx is just e to the x. V equals x minus 1 to the half. So dv dx is 1 half times the derivative of the bracket, which is just 1. X minus 1, take 1 away from the power. So it's 1 on 2 root x minus 1. Because that's negative. Stupid thing, stay still. We know it goes on the bottom. And that 2 goes on the bottom, so we've got a 1 on top. So our derivative is f dash x equals e to the x times root x minus 1. So that's those two. Then I've got to multiply these two together, plus e to the x times 1 on 2 root x minus 1. Maybe I did do this, I can't remember. If we put it over a common denominator of e to the x root x minus 1 times 2 root x minus 1 on 2 root x minus 1, so I'll put it over a common denominator, plus e to the x on 2 root x minus 1. Okay, from here those two join together and we get x plus 1, because root x minus 1 times root x minus 1 is just x minus 1. So I get 2e to the x plus minus 1. That's those two multiplied together, plus e to the x on 2 root x minus 1. Maybe I did go through this. And then from here, we're going to get 2x e to the x minus 2e to the x plus e to the x on 2 root x minus 1. And of course, you can take out, these two join. So we're going to have 2x e to the x minus e to the x on 2 root x minus 1. Then we can take out an e to the x, 2x minus 1 on 2 root x minus 1. Okay. If you missed that, Paddy or Josie, you can go back and rewind the video. Okay, so here, now I'm going to do it the way that I usually teach as well. So f dash x, I derive that, so I get 4x, and leave that one alone. Sine 2x, and then I leave this one alone, so 2x squared, and then I derive sine 2x, and when I derive sine 2x, I get 2 cos 2x, and then we clean up. 4x sine 2x, 2 times 2x squared is plus 4x squared cos 2x. If you wanted to, you could take out 4x, sine 2x plus x, because I've taken out 4 on one of the x's, cos 2x. So that's it, derived. Okay, this one here, f dash x, let's derive this. So when we derive cos for x, we get negative 4 sine 4x. I think my pen's still too big. Okay, so f dash of x is derive cos 4x, we get negative 4 sine 4x, and we leave sine 2x alone. And then we get plus. Now we leave cos 4x alone, and we derive sine 2x. We know when we derive sine 2x, we get 2 cos 2x. So we end up with negative 4 sine 4x sine 2x plus 2 cos 4x cos 2x. And you can't add them together. That's not sine 6x. No, no, no. It just means that this angle is twice as big as this angle, but you can't just add them together. There is ways you can add them together, but we don't need to know that in methods. So you just remember you can't add those two angles together. Okay, I've got another couple. So why does it keep disappearing? Okay, so f dash x, derive this, 2e to the 2x, and leave the sine 2x plus 1 alone, plus, so I derive that, leave that alone. Now I leave that alone, and then I derive the sine 2x plus 1, which we know when we derive sine 2x, we get 2 cos 2x plus 1. So we end up with 2e to the 2x sine 2x plus 1 plus e to the x, forgot the 2 inside, 2e to the 2x cos 2x plus 1. Then from here we can take out 2e to the 2x. We get sine 2x plus 1 plus cos 2x plus 1. So that's it, factorised. Don't forget you can always go back and check on your cas. So e to the 2x times sine 2x plus 1 plus 1, highlight d dx, simplify. So 2 e to the 2x, so I don't know why they did that, but the 2 and then e to the 2x, and then inside cos 2x plus 1 plus sine 2x plus 1, so exactly what we got. Okay, this one here, dy dx, let's derive that. We get 2x and leave that alone, log ex. Then leave the x squared alone and derive log ex. Now we know it's the derivative of the bracket, which is 1, on the bracket, which is x. So you get 2x log ex, and then plus x squared on x is just x, but we know x can't equal 0 because we've gotten rid of a 0 on the bottom. We've gotten rid of an x on the bottom. We know it can't equal 0 anyway because you can't log 0. Is undefined. So that's why it can't equal 0. It actually has to be greater than 0. Okay, so now there's another rule which some of you will have seen before, especially the special kids. If I want to derive a function divided by another function. Now this is the one where the order really matters because you can see here that v is first and there's a minus in the middle. So you always have to, v is the bottom thing. So v is always the bottom thing. V always comes first on top and it's always squared on the bottom. I like using this rule. So v times u dash minus u times v dash on v squared. So in this case here, we say u over v, f dash x is v u dash minus u v dash on v squared. So here, f dash of x is v, which we know is x squared plus 4x plus 1, times u dash, which is 1, minus u, which is x minus 2, times v dash, which we know is 2x plus 4, all on v squared, which is x squared plus 4x plus 1 squared. Now don't expand that, because usually you set it equal to 0, and when you multiply it across, it's just going to disappear. So there's no point expanding it. On the top though, you should clean it up. So on here, I'll just write here so that you know. So that's u, that's v dash, sorry, that's v, that's u dash, that's u, that's v dash, and that's v squared. Now, if we expand it, x squared, this is all just times 1, so x squared plus 4x plus 1. Now, I'm going to put a minus and a big bracket around and expand this. X times 2x is 2x squared. Plus 4x, minus 4x, and then minus 8. Now we know they're going to cancel on x squared plus 4x plus 1 squared. So they cancel. So I've got x squared minus 2x squared, which is minus x squared. I've got 4x minus nothing. And then I've got 1 minus minus 8, which is 9, on x squared plus 4x squared plus 1 squared. And that's it. So we can check it, x minus 2 on x squared plus 4x plus 1. X minus 2 on x squared plus 4x plus 1 ddx. So negative x squared plus 4x plus 9. It's exactly what we got. Okay, this one here, u, v. We know that our rule f dash x is v, e to the 2x plus 1, times u dash. When I derive e to the x, I just get e to the x, minus, so v times u dash, u times v dash. So when I derive this, I get 2e to the 2x, all on v squared, e to the 2x plus 1 squared. On top, e to the 2x times e to the x is e to the 3x, because we add the powers. 1 times e to the x is e to the x, minus e to the x times 2e to the 2x is 2e to the 3x, all on, so I added the powers again, on e to the 2x plus 1 squared. I've got e to the 3x minus e to the 3x, 2e to the 3x. So I'm going to put my e to the x first because it's positive. I'm going to say minus e to the 3x on e to the 2x plus 1 squared. If we wanted to, we could take out e to the x as a common factor. So 1 minus e to the 2x. On e to the 2x plus 1 squared. So that's our derivative. And assuming I didn't stuff it up, e to the x, e to the 2x plus 1, e to the x on e to the 2x plus 1, derive, simplify. Let's use the difference of 2 squares on top and taken out e to the x, but it is exactly the same thing. Okay, sine x on x plus 1. So we have u on v So f dash x, v times u dash, which we know is cos x, minus v u dash, u, which we know is, not u dash, u, which is sin x, times v dash, which we know is 1, on x plus 1 squared. Now, if we multiply it out, x times cos x cos x times, or 1 times cos x is cos x, minus sin x on x plus 1 all squared. There isn't a hell of a lot you can do with that. It's probably just better to leave it as x plus 1 cos x minus sin x on x plus 1 squared. Let's have a look. So sin x on x plus 1 x cos x minus, or plus cos x minus sin x. So it's exactly what we got on that line. It's the same thing. Okay, let's have a look at this one. U on v. Okay, so dy dx is v x squared times u dash. Now we know the derivative of, if you need to write it down, that's 1 on x, and the derivative of that is 2x. So I get v times u dash minus u times v dash, which is just going to be 2x, all on x squared. So x squared times 1 on x is just x, minus 2x log e x on x to the power of 4. We can take out x as a common factor. So x 1 minus 2 log e x on x to the 4. That will cancel with one of those to make it a 3. So I get 1 minus 2 log e x on x to the 3. And of course we know x can't equal 0. So that's the product rule and some quotient rule, which we had already done. So sorry about the double handling. Okay, so this is the last stuff of the chapter, and it's called limits and continuity. So we know what limits are because we looked at them before, but trying to work out whether something is continuous or not, we need to work out whether if we graph this function, if it would join up. So if we look at this thing here, I've got a function, 2x and negative 2x plus 1. The point we really need to look at is 0. If x equals 0, we get the top one. The top one, if I put 0 into this, I get 0. And if I put 0 into negative 2x plus 1, I get 1. So because they're two different values, we would say f of x is discontinuous at x equals 0. Because if we were to sketch this graph, 2x, negative 2x plus 1, I can go into here, put in a hybrid function, 2x, negative 2x plus 1, x is less than or equal to 0, x is greater than 0. Sketch it. You can see at that point there, they don't join up. So if something is discontinuous, if you draw from left to right, so if we went to draw this, it'd go up like that, there's the graph, then we'd have to take our pen off the page and then we'd draw that other bit. Because we have to take our pen off the page here at x equals 0, then we know it's discontinuous at x equals 0, i.e. the graph isn't continuous, we've got to take the pen off the page. Now if the original graph is discontinuous, then that also means that the derivative is also discontinuous. Now, just because the first one, because that's continuous, doesn't always mean the derivative is continuous either. Now, these things stuffed up. I don't know what they are. Okay, so the next graph, x squared, if we were to sketch that for x is greater than or equal to 0, that's going to look like that coloured in and look like that. But if I do negative 2x plus 1, that's going to go through 1. And it's going to have a downward slope because it's negative. So it's also discontinuous at x equals 0, and therefore f dash of x is discontinuous. So the derivative doesn't exist at that point, and neither does the function. This one here, at x, if we were to sketch it, when x equals negative 1, in this graph, at equals negative 1, if I put negative 1 into here, I get positive 1. So because there are two different y values, we can say x is discontinuous at x equals, no, f of x is discontinuous at x equals negative 1. And then we test at 0. If I put 0 into here, I get 0. And if I put 0 into here, I get 1. Because they're also two different values. And at x equals 0. Everything else that's continuous, like x squared, that, like when x is greater than, sorry, if x is, that must be less than negative 1 or equal to. That must be greater than or equal to 3, or 0, sorry. So because it's discontinuous at those 2 points, the gradient's also discontinuous at those 2 points. Like it doesn't work. Let's try here. The only place it could be discontinuous, because they're continuous functions, is at 0. So if I put f of x, if I put 0 into both of them, in this one I get 1, and in this one I get 1. So that means it's continuous for all x. Now that doesn't mean the gradient's continuous, so let's find the gradient. The gradient also, for it to exist, it has to join up like the whole way through, it has to be continuous. So f dash of x is 2x and negative 2. Now, if we put in x is greater than 0 and x is less than 0, if I put 0 into this, I get 0, and if I put 0 into this, I get negative 2. So, whilst the original function is continuous for all values of x, f dash of x does not exist at x equals 0. So the gradient doesn't exist, but the original function does. And I'll show you why. X squared plus 1, negative 2x plus 1. So x squared plus 1 and negative 2x plus 1. Now if you have a look at this graph, when it gets to the point where they join up, if you look at the graph, you can see here that whilst they're continuous and they join up, the point where they join up, I can't tell whether the gradient, if I come from the left-hand side, the gradient might be 0, but if I come from the right-hand side, the gradient might be, say, negative 2. Because they've got two different gradients, which one do you use? You don't know which to use, so you can't use either. So let's see, I don't know if this will allow us to, if we can derive this function. So if I said d dx, never tried this before. Okay, it didn't like that. Okay, so let's graph it. So I've got 2x given negative infinity is less than x, which is less than 0. And I've got negative 2, because these are the derivatives, given x, 0 is less than x, which is less than infinity. If I sketch them both, you can see that they don't join up. So because it's discontinuous, the derivative doesn't exist at that point. So whenever you have a cusp or like a sharp point, which is what we have on the original graph. So this point here, that's a sharp point or a cusp, like it doesn't join smoothly. It's never going to join up. It can join smoothly. I've written a function as well that does. Oops, wrong thing. Okay, so this equation here, original function, when I put 0 into this, I get 0, and when I put 0 into this, so it's continuous. The function is continuous for all x. Now let's have a look at the derivative. So f dash of x, if I derive that, I get 1. And if I derive the second bit, I get negative 2. So they won't join up because they're two different values. So it's discontinuous. It's not, the function is not derivable. Does the derivative is not defined at x equals 0. It is everywhere else, it's just at the point where they join up. Because they don't join smoothly, it won't work. Now, here's a graph, look at this rule. So find f dash of x and sketch it. So if we said find f of 0 in both of those equations, in the top one we get 1, in the bottom one we get 1, so we say it's continuous. Continuous for all x. Then if we say f dash of x, we're going to get 2x plus 2, and we're going to get 2. If x is 0, in the top one we're going to get 2, and in the bottom one we're going to get 2. So they join smoothly. So if we sketch it, 2x plus 2 when x is less than 0, so it's going to go through 2, and it's got a gradient of 2, so it's going to look like that. So that's y equals 2x plus 2. And then the other graph is y equals 2. So you can see here, when I graph dy dx versus x, I could draw this without taking my thing off the page. And the original function, I can also, it's continuous. So because the original function is continuous, and the derivative is continuous, then we can say this function is continuous for all x in f of x and f dash of x. So the derivative exists for everything. Okay, so here's another one. For the function with rule, find f dash x and find the values of x for which it is defined. So f dash x is 2x plus 2, and it's also 1. If x is less than 0 and x is greater than 0. Now if we put 0 into this one, I get 2, and if I put 0 into this one, I get 1. So you can say it's discontinuous at x equals 0, therefore not defined at x equals 0. So find the values of x which it's defined. Now if we sketch it, we've got 2x plus 2, so it goes through 2. Always draw it with an open circle to start off with. And it's got a gradient of 2, so it's going up like 2. And then you colour it in if it joins up, but in this case, because the other one's 1, which is there, it doesn't join up, so we can say the derivative is discontinuous when x equals 0, because that's x equals 0 there. So that's dy dx versus x. Okay, so the function would rule that. State when the derivative is defined and sketch the graph of the derivative function. Okay, so Let's find dy dx, or f dash of x. So we're going to get 1/3 x to the negative 2/3, which is 1/3 on x to the 2/3. Now, if we were to sketch x to the 2/3, we did this earlier this year. X to the 2/3, so I know it's 1 on, but we just sketch x to the 2/3 for a start. If I put a positive number in, if I square it and then cube root it, it's going to go downwards, so it's going to look like that. If I put a negative number in and I square it, it's going to become positive, and then when I cube root it, it's going to look like that. So that's the graph of x to the power of 2 on 3. Now, if we do 1 on that, what happens is, we know that it's 0 there, 1 on 0 is undefined. A really small number, 1 on a really small number is a really large number. 1 on 1 is just 1, and 1 on a really large number is a really small number. So this is my derivative, and it'll be the same on this side. So that's, I should have done that. That's an asymptote, y equals 0. So state where the derivative is defined and sketch the graph of the derivative function. So the derivative is defined for all x except x equals 0, because that line is undefined. And we can sketch it, just so you know that I'm not fibbing here. X to the power of 1/3, and then we can sketch the derivative of it. Okay, so that's x to the power of 1/3, the blue graph, and then the derivative, you can see how it looks like I just did. It's got an asymptote at 0, and the reason the derivative doesn't exist, if you have a look at the point 0, if I asked you what the gradient was there, it's going straight up. So it's undefined because it's going straight up. Like, it doesn't actually have a slope. Okay, we're just about finished. Sketch the graph of y equals f of x if f of o equals 1. Okay, so let's have a look. So what we do is we put in all of our important points. So if f of 0 equals 1, so that means it goes through 0, 1. dy dx equals 0 when x equals 2 and negative 2. So at negative 2 and at 2, we've got a flat gradient, so it's flat. When the gradient between negative 2 and 2, so in between these 2 points, is negative, so it's got to be going down between those 2 points, and then it flattens out. So here, it's got a 0 gradient at there and 0 gradient here, so now it's got to go down and then like that. Okay, the gradient is positive when x is less than negative 2, so it's got to go down like that. And the gradient is positive when x is greater than 2, so it's got to look like that. Okay, so let's see if everything holds. F of 0 is 1. Yeah, it is. The gradient equals 0. It's a turning point when x equals 2, negative 2. So there it's 0, and at 2. The gradient's negative, because less than 0 is negative, between negative 2 and 2, so there's a negative gradient, sloping downwards. The gradient is positive, sloping upwards, when x is less than negative 2, so there x is less than negative 2, and there. Now you might say, oh, hang on a sec, we don't know what these turning points are. Well, it doesn't tell us. So basically, you could have any curve. You could also have a curve that goes up like this, and come, as long as it goes through there, and as long as it has a turning point at 2, they can't mark it wrong. You could also, if you wanted to, you could go like up like that, go through there, down like that. That's also right. They're all right, because it's like a family of curves. You can't tell exactly what it is. Okay, so as long as you fill out all this information, f of 0 is 1. It's got a gradient of 0 when it equals 2 and negative 2. The gradient's negative between those values and positive otherwise, then that's fine. Okay, so we can finish off chapter 9 and hopefully start chapter 10 on Friday. I hope you enjoyed your digital delivery day via YouTube. Good luck with the exercise, and I'll be online to help when we have class in Teams. So just ask me questions in there. Okay, bye.